Hello, good evening.
Good evening.
Okay, so I welcome you again in this second live session of Ultrafast Laser Spectroscopy course. This is Shruti, and I am the PMRF TA of the course. I'm a PhD scholar in the Department of Chemistry, IIT Bombay. So let's start. So have you watched the first week's lecture?
Yes.
Okay, so let's start. First week is also not that difficult regarding the questions. Okay, so the first question is, a laser spectrometer has superior resolution than an ordinary spectrometer.
1 second. I think week one assignment is yet to be submitted. Last date I think is on 7th, yesterday, tomorrow. So
Oh, is it?
yes, I think so. You can check actually. So
Okay. But I thought it's like it goes
yeah,
on.
generally it is 1 week at a time, but in the first week generally they give 2 weeks time. So both the assignments have to be submitted tomorrow.
Oh, okay. But it's okay. I did not prepare for the extra questions, so let me discuss this only then.
Okay.
So, yeah. Okay. So the first question is about the superiority of a laser spectrometer instead of any other light source. So why is it that a laser spectrometer is so like much useful than a ordinary light source? So we discussed last week like lasers are monochromatic and they are directional and they are coherent. So the answer is same here itself, that First of all, not all lasers are pulsed. So first option is wrong. Okay. So only specific lasers are pulsed. Otherwise, we have continuous wave lasers as well. So this cannot be a specific reason for the superior resolution. We can get the same resolution using a continuous wave laser, not the same resolution. Maybe we can, a continuous wave laser can also serve a purpose in spectrometer. We don't need a pulsed laser as such. Next thing is uh, coherent. So coherent, as I told last week, that the pulses or the beam in the laser are, they move in a particular direction and they are in phase. So that's what coherence means, that beams are in phase. Beams or the light waves, electromagnetic waves, they are in phase plus directional in the direction of polarization. Okay, so this is a good property. Next one is highly monochromatic. Highly monochromatic means the FWHM is very narrow. Almost single wavelength, we can say. So that's why we have lasers with named with a particular wavelength. For example, we will get laser 405, 488, 476, like that. So the lasers will be named after the wavelength which they emit. Okay, so this is a good property regarding the spectrometer, so fluorimeter. So that if you use a laser, you can directly excite at a particular wavelength. Excite at a particular wavelength. So this can be a reason. Also the intensity. So since the laser, the beams are coherent and directional, so the power is not diverging out. So power does not diverge. So the beams move in one direction. So all of the power is concentrated in that particular direction. That's why it is intense. Also, the lasers are produced. Its lasers full form is, there is a term called amplification associated in the laser. Light light amplified stimulated emission of radiation. So anyway, it is amplified light. The light travels many times into the cavity of the laser before coming out. So the intensity is more for lasers compared to ordinary light. So this is also a good property regarding the spectrophotometer. So these three, the last three options, coherent, highly monochromatic, and intensity, can be the desirable properties. But since the question is like single select option selection, so we can go with the highly monochromatic because this is the most important property regarding the fluorimeter. So if you use an ordinary light source, a halogen lamp or something, you will not be able to excite the sample at a particular wavelength. So highly monochromatic nature of the lasers is the most desirable property, which gives it the superior resolution. Okay. So the next question is, from the theory of chemical dynamics, the fastest possible chemical process is expected to have a rate constant of the order. Also, so did you solve this question, Nivid? Hello? Hello? Okay. So to solve this question, we are going to use the Van 't Hoff equation, okay, which comes from the ACT, activated complex theory, and it gives, suppose we have uh, this is the potential energy and this is the reaction coordinate, and this is the energy level of reactants and this is the energy level of product. So this is the activation energy required for the reaction. Okay, this activation energy is given by this equation, kBT by H. Kb is the Boltzmann constant, T is temperature, H is Planck's constant. Q star, Qa, Qb, e to the power minus Ea by RT. Now Q star, here Q's are the partition function. Q star is the, you might have studied these terms in StatMac, the partition function of the activated complex, not of reactant, not of product, of the activated complex. And Qa, Qb is for the reactant and product. Okay, so for a fastest possible reaction, there should be no barrier. So if the reaction goes like this without barrier, this will be the fastest possible reaction. So Ea should be 0. Ea will be 0, which means there should be no barrier, barrierless reaction. Okay. Also, we need to make this term equals to maximum. So it's a ratio, it can be 1. So all the partition function terms equal to 1. So that maximum rate constant, which is K max, will be given by kBt by h. Here other terms are 1. E to the power minus 0 will be 1. Okay, so we have the fastest rate constant will be given by kBt by h. Now kb is the Boltzmann constant. So its value is given by 1.381 into 10 to the power minus 23. And if we are taking room temperature, the question says, I think, the fastest possible. Okay, it's not written the temperature, but let's take generally at room temperature. So room temperature is K divided by the Planck's constant, 6.626 into 10 to the power minus 34 joule second. So if you do the calculation, I think this comes around 6 into 10 to the power 12 second inverse. So the question asks about the order. So order will be it is 10 to the power 12 second inverse. Okay, so for this question we have been given order 10 to the power 12. Since it is only dependent, these two terms are constant, it is only dependent on the temperature. So it will increase this temperature, the rate constant can be increased.
Can rate constant go even higher than this if temperature increases?
Yes.
Keep on increasing a very huge temperature.
Yes, that's what I'm saying, that since these two terms are constant, this is a constant and this is a constant. So if we do the reaction at higher or the at most higher possible temperature, then we can increase the rate constant. The maximum possible rate constant can be achieved by increasing the temperature.
But in that case, it cannot be called K max, right? Because if temperature increases, then it won't be 6.2.
Let
It
me
can go
write
even
this
higher.
as Kmax at 300 K.
Okay, K max at 300. Okay.
But there is always a limit at the maximum temperature we can reach for doing any reaction. Maybe at that, there we have to see the stability of reactants as well. So this is a theoretical question, like at what is the maximum theoretical limit possible? Okay, so the next question is 10% of light incident on a sample is absorbed. Absorbance of the sample is. So this is related to the absorption. So suppose this is a cuvette and it is a sample inside, and I have shined I0 light upon it, and this absorbs 10% of I0. Then the I will be given by 90% of I naught. Okay, so this is 0.9 I naught. Then absorbance is log I naught by I. So if I'll simply plug the values, I is 0.9 I naught, and if you'll do the calculation here, it will come as 0.045. So it's unitless quantity, it's absorbance. So the absorbance of the sample will be 0.045. So this question was a simpler one. The correct answer is 0.045. Okay, let's move to the next one. So the next question is, for a fluorescent sample and a reference, the emission and absorption parameters are given. So absorption at excitation wavelength is given as AS and AR for sample and reference. Intensity of fluorescence, so the intensity of emission is given, and the quantum yield is denoted as phi S and phi R. So we need to calculate the phi S. So how we'll express phi S? Now let's first see the quantum yield for the sample. For the fluorescence quantum yield of the sample will be given by number of photons emitted from the sample divided by the number of photons absorbed. So it's kind of the efficiency. Okay, so number of photons emitted is this one, emission, and number of photons absorbed, let's write it as absorbance for the sample, intensity of absorbance for sample. Okay, similarly we can have an expression for the reference R, emission. So this is an indirect way of measuring the quantum yield using a reference. Okay, now the unknown quantity here is this I, intensity of absorbance. We need to calculate this one. So, and we need to eliminate that term to get the expression in terms of intensity of emission only. So absorbance intensity can be calculated from the expression of absorbance, log of I naught by I, which we just used. IT, let's write IT for transmitted intensity. So it can again be written as transmitted intensity will be the total intensity shined upon the sample minus the absorbed intensity. Okay, now I can, this is log to the base 10, so I can write it like this, taking anti-log. Now let's take, since we need this term, so let's take reciprocal. Okay, now you can separate this factor. So like this we will get the expression for the absorbed intensity. Okay, now suppose the same expression I can write for sample absorbance of the sample AS, and for the reference here it will be I naught only, because the excitation source should be same for the sample and the reference. Minus AR, R denoting the reference. So the ratio, let me write this as fluorescence quantum yield of the sample divided by fluorescence quantum yield of the reference will be, as we wrote here, emission intensity divided by absorption intensity. So it will be divided by, and for the reference it will be reciprocal. Now plug in the value of intensity of absorption which we calculated now. Okay, now this initial intensity, excitation intensity is cancelled, and we can get this intensity of emission of the sample divided by intensity of emission of the reference into 1 minus 10 to the power minus AR divided by 1 minus 10 to the power minus AS. So this is the expression. So you can have quantum yield of the sample into this factor into the quantum yield of the reference. So this will be the final expression. Okay, let's see. So we have on the numerator, so I think the answer is D. Okay, and out of these three things, what we will measure, this should be known earlier, or the reported value, and all other things, sample absorption we measure, then this whole thing can be measured. Okay, so likewise, by getting these four factors and knowing the quantum yield of the reference from previous reports, we can calculate the quantum yield of the sample with respect to the reference. So this is an indirect measurement. And for the solution, we need to also add terms here like refractive indices if needed. So the expression gets more complex. We add the refractive index term. So the refractive index of the sample and the reference if you are using two different solvents. Okay. Some standard references can be, suppose, rhodamine dye. It has a quantum yield of 0.9, very high. Fluorescein dye. This also has a quantum yield of 0.95. So these can be the references we can use to get the quantum yield of our own sample. But here in the indirect measurement, we need to take care that we should use the same instrument. We should use the same instrument to do all the measurements of the sample and the reference. If you will use the same instrument, keep the excitation source same. Keep slit widths or the detector, everything same. Okay, so likewise you can get the quantum yield of your desired sample. Okay. So let's move to the next question. Usually a modern scanning monochromator contains prism, grating, slits, curved mirrors. So it is asking about modern monochromator, uh, scanning monochromators. Now what is a monochromator? What is a monochromator? Can you answer this?
Yes, monochrome. I mean, the light is polychromatic, so it splits out the light into many different wavelengths. It can be used with excitation and emission both.
Yes. So a monochromator is a instrument, the part of a spectrophotometer, which allows to choose the wavelength or to separate the wavelengths. So in the excitation monochromator, it will allow you to choose one particular wavelength to excite your sample with. And the emission monochromator, as you can see here, this also will allow a particular wavelength to get detected. Okay, so inside the monochromator, what is the instrument or the device which allows us to choose or to separate the wavelengths? So Now, we have all seen that a prism is a device, or we know this like from our high school knowledge, that when you shine a white light over it, it it disperses it into 7 different colors, right? So this is also a kind of separation of wavelengths. White light or sunlight. So this thing, the prism can also act as a monochromator. Okay, but in the modern day instrument, we don't use prisms. Actually, we use this kind of transmission or reflection gratings. We use slit or we used curved mirrors. So for this question, the correct answer is 2, 3 and 4. But the prisms are not being used anymore. The disadvantages regarding prism was like this. So what is a prism made of? Prisms are made of glass, okay, and glass will also absorb, also have some amount of absorption in the UV region or so. So the disadvantage is when you will excite or shine light upon the prism, it will absorb some amount of it, and the intensity which you will get after the separation will be very less. So since this side is a mixture of many wavelengths, so here anyway intensity is going to be high, but after the separation of particular wavelength, the intensity is going to go down because the number of photons are being segregated in each particular wavelength channel. So if the glass or the material of the prism is again absorbing something, the intensity will even lesser of the output. So that's why it's one of the disadvantage, because glass, some amount of light. Okay, and one more thing is that this dispersion is not linear. Dispersion is not linear means that there will be more dispersion of the shorter wavelengths. Increases for shorter wavelength, which means we will have shorter wavelength violet here, red here. So red, from the actual light path, red has been dispersed the least and violet has been dispersed the most. So it's not a linear relation. Each wavelength is not being dispersed by equal distance. So this is also a disadvantage. And one more thing can be the refractive index difference. So there will be, the light can experience different refractive indices based on the wavelength. Dispersion will is what dispersion is due to the difference in the refractive index of the material for a particular wavelength. So these are the disadvantages for the for use of prism in the monochromator. So now these days people mostly use gratings and slits. So what these two things are doing, so you have a light source here and you put a slit in between. Okay, so this slit distance is very less in microns. Okay, and then in front of the slit, you put a grating. So a grating is a substrate, or it's a thing which has many lines etched on it. So it may have 70 lines per mm or 300 lines per mm or 600 or 1200, depending upon the quality of the grating, or 1800. So if the number of lines increases, we will have more resolution. So the difference between the two wavelengths will be more resolved. Okay, so when the light goes through this slit, the slit can be controlled. So we can have, so we are allowing, suppose the beam is this broad. So we are allowing a part of it to go through. So goes through this, and then upon hitting the grating, so this is transmission grating, it will neither absorb anything, it will simply transmit all of the light, but it will distribute the wavelengths. Oh, I don't have violet color here. Okay, red is gonna go down. So red, and this side will be violet. So here you will have 400, here you will have 700 nanometer, and all of the wavelengths will get distributed. So the difference between the resolution, suppose the resolution is 0.5 nanometer or 1 nanometer or 2 nanometer or 5 nanometer, this is decided by how many lines you have on this transmission grating. Depending upon your use or the instruments need, we choose the grating. So this is how this modern days monochromator works, and all this process is like controlled by the software. So you can change this slit width. The slit width parameter which we adjust via the software is this slit width. Okay,
The slit width also has a role in the wavelength resolution.
yes. So if the slit width will be very large, the separation of the wavelength will not be fine enough.
Okay.
Yes.
Usually, I think I remember in one of the fluorimeters we used, I don't know what the unit was, probably it was nanometer. We used slit
Yes,
width of
unit
5.
will be in nanometers. Slit width
Is
unit.
split with the same is the same thing like band pass, or are they different?
Yes, yes, the band pass.
They are both the same.
Yes. Some software it writes like slit width, or some will write band pass.
So basically, the idea of adjusting the slit width in any of the experiment is to do with the wavelength resolution.
Yes. So there will be options in the fluorimeter like 1 nanometer, slit width 2 nanometer, say 8, 16, 32. 32 is way too big slit width. So we generally keep it max up to 5 nanometers.
Oh, the only I think basically slit width all has to do with the resolution only, nothing else.
Yes. Okay. So
You said a curved mirror can also be used, but I have not seen anything like that. Curved.
curved mirrors, I have also not seen any with curved mirrors, but curved mirrors are, yeah, I don't know exactly how the curved mirror ones will work.
Can be used nevertheless.
Yeah, can be used. Mirrors have advantages over lenses for some instruments. So because
They
lenses
will
work
not
in,
no, not absorb the light, right?
yes,
They will not pass through.
it will not pass through. It is a reflection mode geometry. So maybe in some instruments where we have very less light or like that, maybe we can use curved mirrors. Again, we have to use it with some kind of grating to separate out the wavelengths. I think so. Okay. So shall I move to the next question?
Yes.
Okay. So this question is about, in order to get a good spectrum, speed of acquisition should be fast, averaging time should be long, slit width should be small, concentration should be extremely high. So there are many factors we have to take care in order to get a good spectrum. Like considering only one will not work. So suppose the first one is speed, scan speed. Scan speed means how fast you change your wavelength. Suppose suppose your emission is like this, maybe 545 nanometer. Okay, so how fast you move from one wavelength to the other, what is the speed of acquisition, like integration at a particular wavelength. So the signal at the signal at 400 and at 545, there is a huge difference. This is very small and here it is very large. So if your scan speed is very fast, this will anyway get detected, but there might be noise over this wavelength, isn't it? Because here the signal is so much, the emission is so much, so we need to take care of the integration time. Integration time or acquisition time, this is the time for which the signal gets collected. Suppose it will be 0.1 second or 0.2 second, like that. So the detector for will stop at one particular wavelength, so the signal will get collected for 0.1 second to generate a spectrum at 400 nanometer. So at each wavelength, it has to wait for 0.2 seconds and the signal will be the average signal for that particular time. Since this emission, it's the emission will come in, the fluorescence will come in nanoseconds, right? But we are waiting up to seconds to get enough photons so that we can have a sharp signal even at the wavelength where we have emission, lesser fluorescence, so that the signal to background ratio or the noise is not much. Otherwise, it may generate something like this here, like this. Okay, So depending upon the sample, we can change the speed of acquisition. We have to play with it, adjust the parameters. So this is one thing. Next is the averaging time should be long. Now averaging time is more or less related to this only, or how many spectrums you collect and average it out to make a one single spectrum. Suppose there are parameters in the fluorimeter which says that you take means one scan means you take a scan like this. Okay, you take where you can put it like 10 scans, so you will have something like this 10 times and so on 10 times, and then you will get an average of all the scans. So this is the average. So this is averaging time. So how many scans you want to average out? This also again depends upon the type of the sample. If the sample is very emissive, we can keep it only one scan or two scan, or simply one scan will work. But if the sample is not very fluorescent, the signal is very less, we have to average it more number of times. So averaging time should be long. But yeah, if we keep the averaging times long, maybe 10 scans, 50 scans, then it will take more time to generate the data. More time to generate the spectra. So depending upon your sample, we need to adjust this parameter. Next thing is slit width. As I just told, slit width should be small.
I have a question. You mentioned two parameters, speed of acquisition and averaging. I mean,
Yes.
which one will be better to spend time on? Uh,
It actually whole thing depends on the sample, how good your sample, how emissive it is. We Whenever we go and take emission spectra, we play with the parameters, keep one constant and change others to see like at what parameters we are getting a good spectra, so we can have less noise in the data.
okay. So
Yeah.
some hit and trial is needed before we
Yes, yes.
finalize.
So at first, suppose you keep 0.1 second or one scan, then you see keep the integration time constant and increase the number of scans. See whether the data is getting better or not, or like that. So generally, what we do, uh, we keep this integration time as 0.1 second and scan to one only, one or two, and we play with the slit width. So slit width can be increased or decreased. There will be options like 1 nanometer, or it goes up to 32 nanometers. But we
But for
never keep.
the spectrum, generally, I don't. It will not it be good idea to keep the slit width to the minimum so that the resolution will be maximum.
Yes,
For
resolution will be maximum, but there will be very less photons. If the slit width is 1 nanometer,
okay,
the,
noise. So
the
noise will increase.
there will be very less photons. So the noise may increase. So you can keep slit width 1 nanometer only if your sample is highly emissive.
Okay.
Yeah. It all depends on the property or the quantum yield of the sample. We cannot fix one thing for like it cannot be universal for all the samples. Okay, so yeah, that's what I said. Like there is a what I call is a optimum value all the parameters for a particular sample. Okay, to get the data, the quality of the data you want. Now, next thing was the concentration should be extremely high. Though concentration should be extremely high is not generally needed. It will not depend on the concentration much. Maybe the signal will get enhanced for the concentration, but there can be other nonlinear effects happening if you increase the concentration much. So it is always advised to keep it to micromolar concentration, micromolar or to millimolar for to get the fluorescence. So to answer this question, we can have these two parameters. We can play with these two parameters, the averaging time and the slit width. The speed of acquisition, it is written fast. We cannot integrate fast enough so that we don't get enough number of photons. So it it also needs to be optimized, some optimum value. If it will scan fast, there will be more noise. Okay, so that's it. That's the answer. The answer should be B and C only. And regarding this slit width, suppose you are taking a spectra at 32 nanometer. So your actual spectra might be looking like you have peaks like this, but when you are considering the slit width 32 nanometer, maybe all the peaks will get merged, and it may generate something like this because there is no enough separation of the wavelength to make the peaks visible. Okay, so we generally don't keep it, we try to keep the slit width around 5 nanometer or lesser than that. Okay, now let's move to the next question. So it's about the fluorescence excitation spectra does not match the absorption spectra when the sample is. Okay.
I have just a query actually. This slit width, if we say 5 nanometer, does it means delta lambda is 5 nanometer or difference is 5 nanometer resolution, or is it just a physical thing?
No, I think it's just the physical thing.
It has nothing to do with delta lambda because that also comes into the same order nanometer, 5,000 or something. So it's not that 4995 and 5005.
Okay, I'm not exactly sure.
Hmm.
Okay, I will clarify this in the next session. I'm not exactly sure whether it's like
Thank you.
yeah,
That will be better.
yeah. Okay. So, okay, this is about the excitation spectra and the absorption spectra. So we generally expect that the excitation spectra will be the mirror image of the absorption. So when in the case this thing is not happening, there can be reasons that the sample has impurities and it is a mixture of two or more fluorescent species which we are probing, and it can be a mixture of some fluorescent and some non-fluorescent species. Being solid is not a reason here, because for solids also we can expect that the excitation spectra and the absorption spectra should be mirror image. So this was just simple. If the excitation spectra is not matching, uh, there can be things like there are impurities. So we generally take the excitation spectra to see whether the sample is pure or not. If it is coming a mirror image to the absorption, we can say that there are no other species present in the sample. Is it okay?
Yes, yeah. I think Dr. Datta advised that after every fluorescence experiment, this excitation spectra should be matched with the
Yes.
gamma spectra.
Okay. Okay, so the next question is, for a steady state fluorimeter, a light source would be good light source. Tungsten, sodium vapor lamp, deuterium lamp, or xenon lamp. So I'll simply, so tungsten lamp. So fluorimeter, if it is, so suppose we need a visible emission. Considering a visible emission, visible spectrophotometer in the visible range. So tungsten lamp has 320 nanometer to 2400 nanometer. Okay, so this is the data I collected from internet. And sodium vapor lamps are two wavelengths. This is generally 589 nanometer and 589.6. This comes from the energy level diagram of the sodium. So it emits only these two wavelengths. So we can say 589. Next is the deuterium lamp. This has lesser than 400 nanometer, approximately 180 to 370. And the next one, the xenon lamp, is exactly matching the solar spectrum or the visible range, 400 to 700 nanometer. Okay, so you can say that we can use xenon lamp mostly for the visible range, and for the excitation in the UV we can use a deuterium lamp. UV excitation, and this can be used for visible excitation. But considering only the visible excitation, we can have the xenon lamp. But some fluorimeters will have both the UV excitation and as well as the visible excitation. Depending upon what the excitation source you want, the lamp gets the position of the lamp gets changed. Okay.
The absorption spectrum, yeah. In UV visible absorption, we use two lamps, but in fluorimeter, generally we use only one lamp. Why cannot we use two lamps? Fluorimeter also.
No, we can have two lamps.
You can have. Okay.
Yeah.
Okay.
Depending upon the company, the fluorimeter is of.
Okay.
So we can, if you want UV excitation, you will have to have a tutorial lamp.
Okay.
So the fluorimeter which we have in our department, it has two lamps.
Okay.
next question is about the reflector. So you have watched the videos, right? Can you tell me what a retro reflector is?
Yes. So retro reflector. I forgot which experiment is that, but it is in I think some 11th 12th lecture. It there are one is one light goes directly from the source to the retroreflector. Others goes via the sample. So retroreflector creates a phase shift between these two lights.
Yeah, so in all the pump probe experiments where you have a pump and a probe, you need to have a delay between those two beams. So to create the delay, you will have a mechanical moving stage like this, which moves back and forth. And so if you have a light shining over here, then after the reflection, so if your incident position, if your initial position was here, then the path the light will travel will be more. So the red one is the path length is more than the blue one. So this creates a delay between the pump and the probe. So to create the delay, we need to use this retro reflector. Okay. Now the question is asking, in order to bring a delay of 10 femtoseconds, so there should be 10 femtosecond delay between the pump and the probe. The retroreflector has to be moved by how much? So this mechanical stage has to be moved by some microns to create a delay in the femtoseconds. Okay, so as you have read in the lecture that light will travel, so 1 foot, which is approximately 30 centimeter, in 1 nanosecond. Okay, that is in 10 to the power minus 9 second, it goes 30 centimeter, means 30 into 10 to the power minus 2 meter. So in 1 second, it will go 30 into 10 to the power minus 2 divided by 10 to the power minus 9 meter. Okay, so we need a delay of 10 femtoseconds. So for 10 femtoseconds, it will be just the unitary method. It will be into 10, and femtosecond is 10 to the power minus 15 seconds. Okay, upon the unit cancellation, here second, we'll get it in meters. So this will be minus 17 plus 9, 300. 300 into 10 to the power minus 17 plus 9 meter, which is 300 into 10 to the power minus 8 meter, or 3 into 10 to the power minus 6 meter. Now 10 to the power minus 6 is microns, so the path length should be 3 microns. So the path length should be changed by 3 microns. But in order to change the path length by 3 micron, we need to move the retroreflector by 1.5 microns. Because it's going, hitting the retroreflector and then coming back. So this is S, this is S, distance. So 2S should be 3 microns. So S will be 1.5 microns. So you have to move the retroreflector by 1.5 micron. So that then the delay will be 10 femtoseconds. Is it clear? So here the answer should be 1.5 microns, not the 3 microns. Okay. So the last question for today is, in the electronically excited states. So I think this same question I discussed in the last session. Organic acids become more acidic in excited state, and likewise organic bases become more basic in the excited state. So I have given the reason for the acids. So the same reason is true for the bases as well. So what happens, suppose we have a base here, and in the excited state, so in the first, let's draw for the ground state. This is ground state. In the excited state, the energy level diagram will be okay. So in the excited state, one of the electron has went up. Now this is more easier to attract because this is anti-bonding. This was bonding, isn't it? So this electron is now more basic. It has more basic tendency. Can it can abstract the proton easily than in the ground state, because this was in the stable state. So this is the reason why organic bases become more basic in the excited state. This is the same reason which for the acids. So the answer is 3 here. Both organic acids and organic bases become stronger. Okay. Is this fine?
Yes, it's fine. It just so happens that can you also help me get couple of papers in this regards, as this topic is really quite interesting. So
Regarding these organic acids and bases diagrams.
yes, the acidity and the basicity increasing.
Okay,
So
I will. I
yeah.
don't know. Okay, I will put the papers in the drive. Okay.
Drive. How will I access the drive?
You can actually access these live sessions and these
Yes,
PPT
yes,
from the course page. So if you will open that drive link, I'll simply show you. So this is the drive. The drive link is already shared with you guys. Yes, here. So you have you
no,
from
it's
there you can get
your
the photos
PowerPoint
of
is
the
only
session.
showing.
Yes.
Only your PowerPoint is visible.
Oh, okay, okay. Sorry.
You need to share the screen, I think.
Yeah. Actually, I'm sharing my screen via tab, but it is visible from the. You can just go to the course page in the NPTL.
Okay, I'll
Yeah,
try.
you will get it. Or else you might have got a mail regarding the problem solving session recording.
Ah,
If you will open that page or itself, you will have the drive link and everything.
in the email.
Yes,
Uh,
the email has a link.
there is a groups.google.com. There is announce plus subscribe, and there is one groups.google.com.
Uh, okay, let me. Okay, so okay,
Yes, I can get it. Yes.
yes.
Now log in with Google, is it?
Okay, so here when you will go problem solving session,
Yes, yes.
problem solving this recording thing,
Hmm.
click here, then I think it should give a, yeah. So this is the page and this is the presentation folder link. You will
Yes.
get the presentation, and this is the YouTube video which since the session is being recorded, I upload it in this YouTube video so any other student can watch it later. So
Yes.
in this drive itself, I'll try to put the papers.
Okay. Yeah, put two, three papers, which are the most, yeah, this topic just interests me. So,
Okay, yeah, sure.
2, 3 important papers in this regard. Yeah.
Okay, I'll try to put before the next session. I'll upload
Because
it.
what I can see, the effect is very dramatic. Yeah, this tyrosine from 11 can go all the way to pH, PK, I think 3 or
Yes,
4, which
yes,
is
yes,
8 orders of magnitude.
yes. I think in the course itself, sir has suggested a few references, but if it is not there, I'll just try to upload it by my own.
Okay.
Okay. Okay, so that's all for today.
Yeah, also help me. I mean, I want to know NPTL good course and NPTL about general introduction to lasers and probably fluorescence. There is
Yeah,
one course for fluorescence.
there are courses on lasers. There is one course completely on laser.
Huh.
I can. Uh, can you see my screen now?
Yes, I can see the screen.
So this course, lasers fundamental and application. It is completely on lasers. 40 lectures.
Okay.
Yeah. So if you want, you can go through this one.
I'll just write it down in 1 second.
Yeah,
I can
sure.
screenshot. One second.
Yeah, sure.
Yes, this is by Dr. Prabhajot Singh. So this is on fundamentals and applications of lasers.
Yeah.
Okay, fine.
I have not gone through the course myself, but looking at the content, it seems it is a quite a course. Like everything has been covered.
Okay, especially specifically to do with the spectroscopy part.
It is basically the function and the working of lasers. how the laser, like, it's generated, the physics behind it.
Mhm.
Yeah. Yeah.
Okay, so is the lecture over?
Yeah. Actually, I'm done with the questions for today.
Okay, thank you very much. I will log out.
Thank you.